Hello everybody, good morning, good afternoon or good evening wherever you may be, and welcome to this AWS webinar. This session is an AWS 201 level webinar, so it expects a certain level of understanding of cloud computing concepts and AWS services. So today we will be talking about how to design scalable, available and resilient cloud applications. My name is Markku Lepistö. I'm a technology evangelist at AWS working out of Singapore. Now first, let's take a look at some housekeeping items. The presentation will run roughly 45 minutes or so, and while I'm presenting, please go ahead and use the questions panel in this webinar system for live Q&A. We have our solution architects online here, and they will be answering as many of your questions as they can. And then a reminder, please fill in the survey. The survey is at the end of the webinar because we love your feedback, and we are actually iterating on our services based on your direct feedback. So please let us know. So without any further ado, let's get going. First, a really short, brief introduction to Amazon Web Services. So AWS provides a range of services over the internet as web services. We have a broad and deep set of services that we provide out of our global presence. As of today, we have 10 regions around the world, consisting of 26 availability zones, which are fault isolation zones in the same regions. And as of today, we have 52 edge locations, and the edge locations are providing our global CDN and domain name resolution or DNS services. So today's topic is specifically on scalable, available and resilient cloud applications. What do your users actually want? So if you're making an application for your internal or external customers and users, they probably want things like high speed, fast, high-performance experience for them. They want the application or product that they're using to be always on and accessible anywhere where they have an internet connection. They start to more and more request personalized and rich application features. And they want to see yummy new features all of the time. So they want your application to evolve and give them fresh things and experiences all the time. So all in all, your customers are expecting to have powerful cloud applications. But how? Let's take a look at a rule book, how to build powerful cloud applications. Let's start with rule number 1. Service all of your requests. So the first thing to note is that we have to consider the end-to-end scenario, all the way from your clients, your customers, to the backend systems, and the entire chain. So the first thing is make sure that your customer requests can find your front door, if you will. It's a matter of resolving your host name and your domain name. And if your clients cannot resolve your address where your system is running, your endpoint, then the rest of the system is actually irrelevant. So this is something that should not be overlooked, DNS resolution. And this is where the first service from AWS can help, Amazon Route 53. So Route 53 makes it really easy and simple and cost efficient for you to manage your domain names and your host names at scale. It has 100% availability SLA. It has global presence currently at these 52 edge locations I mentioned, and we are growing our presence constantly. The main thing is that with Route 53, you have high reliability, automatic scalability, and really ease of use of managing your host and domain names. And like everything else, it's a programmable service, so you can automate the domain and host name management as you're deploying or modifying your applications. The next step after resolving your application endpoint and host name is to get to the application itself. So the best practice here, again to have availability, scalability and resiliency, is to distribute your application across multiple fault isolation zones. So we have the concept of regions. For example, here in Asia Pacific we have Singapore, we have Beijing, China, Tokyo and near Sydney, Australia. And in the regions we have multiple availability zones, which are fault isolation zones. They are interconnected by low latency networking, so you can do, for example, synchronous replication of your data within the region. So the best practice here is to distribute your load, your workload and application across multiple availability zones and potentially even across multiple geographical regions. The use of multiple geographical regions could be, for example, for disaster and recovery purposes, or simply to have global scale and availability for your applications near your customer base globally. And here in this picture you can see an elastic load balancer service in front of the region, balancing the load across multiple availability zones. And we will be deep diving onto these topics later in the session today. The next tier, after the application tier, is then your data tier. So the same thing. You want your data tier to be scalable, highly available, and resilient so that you get fast access to your data and you're not slowing down your responses, and that you can access your data and that you don't have failures because you cannot access data in time. So in this particular example here, we are leveraging the Amazon RDS, or Relational Database Service, for SQL-based database engines, which can, for example, give you master and hot standby slave replication of the database so that the master is in one availability zone and there's an automated synchronous replica in another data center within the same region. We have also features called cross-region read replicas, where you can easily replicate asynchronously your master database to a read replica in another region or within the same region. And again, we will be discussing the database topics more in the subsequent slides. But this is an overview picture from domain name resolution to load balancing to application tier and then the data tier itself. Now let's start deep diving a little bit more. Once you have your customers reaching your system and you are serving all of the requests at scale, you want to serve the requests as fast as possible so that your customers have great experience. Again, let's start with the domain name resolution. So with Route 53, there's a really handy feature here called latency-based routing. Now, let's imagine that you're using two AWS regions. For example, region A on the left could be Singapore, and region B could be Tokyo, Japan. Then you have a customer request coming in. It is trivial to configure Route 53 and activate latency-based routing. So in this case, the Route 53 service will see and investigate where the customer request is originating from, and then it will estimate the round-trip latency between your actual customer client and these two regions that you have configured for your service. And in this case, we can see that region A will have a 16 milliseconds, give or take, round-trip latency, and region B will have a longer round-trip latency because it's geographically further away from the customer. And here, Route 53 can then make a decision to point this particular user to the nearest region serving your application, which could be Singapore, for example, in this particular case. You can also configure Route 53 to do health checks to your backend systems and then route your customers to available versions of your system if, for example, one of your system copies has some issues at the moment. So you can combine health checks and latency-based routing, and these are really features that go beyond simple hostname resolution in Route 53. Moving on. Let's say that we have resolved successfully the host and domain name and your customers are accessing your system. They will want to be downloading the assets. They can be dynamic web pages, they can be videos, images, pictures, etc. So here, using a content delivery network can significantly accelerate and improve your customer experience. The service we have here is called CloudFront, which is also served out of the same, currently 52 edge locations around the world. So leveraging CloudFront, you can easily distribute your content to your end users with low latency, high bandwidth, and high data transfer speeds, and no commitments. So let's take a look at this example picture here. You might have some customers who are based in Singapore, near Singapore, maybe some Japanese customers, and maybe some customers in Australia and New Zealand. So first of all, you can resolve the CNAME or host name using Route 53 and CloudFront, so you can easily allocate a nice custom host name and domain name for your entire system. and it can be pointing to the CloudFront distribution. As your customers are accessing your system through CloudFront, CloudFront can then fetch the content from the origins. And CloudFront supports both static and dynamic origin servers or origin systems. So first, let's take a look at the system on the right. Here we have an elastic load balancer, balancing the load across an auto-scaling group of EC2 servers with your application servers, for example. This is called a dynamic origin in this case. They might be serving from, for example, PHP, Node.js, other web pages and sites. And on the left there, on the top, we have Amazon S3, a highly durable, unlimited scale storage system for your objects. It's a handy place for you to store your static assets like your images, CSS files, your video files, etc. So here, we can have CloudFront simply, again, fetch the content from the origin, which could be an S3 bucket or multiple buckets, and then cache the content at the edge locations near your customers. You have full control over the caching mechanisms, so you can set the time to live parameters for your different types of content. Some of your content you may want to cache longer, so that you have less hits in the backend server, and the caching percentage is higher at the edge then. For some of the more dynamic content, you can set a shorter time to live or caching duration. And interestingly, when you use CloudFront, you can basically offload a lot of the traffic away from your backend servers. If you don't use a content delivery network, if you don't use CloudFront, each and every one of your customer requests will actually hit your backend servers. So then you need to scale and serve every one of those requests out of your EC2 servers, for example. But as you introduce CloudFront in front, CloudFront will then consume and serve most of the customer requests, and it will occasionally then get the content from the backend systems like S3 or your EC2 servers. So by putting CloudFront in front of your website, you can both accelerate and improve your customer experience, and you can actually scale down your backend system and save money. So it's both cost efficient and more scalable, and it gives users a better experience. In this slide here, these are based on actual measurements. You can see the effect. The bars on the left show response times and your backend server loads if you don't have CloudFront in front of your system. Then when you introduce CloudFront for static and static plus dynamic content, your customer experienced response times will be significantly reduced, as well as your server load. So for example, auto-scaling can then remove unnecessary servers from your fleet, in effect saving you money. So let's still talk more about caching. In addition to CloudFront, which you can put in front of your entire website, it's also a good idea in some cases, or in many cases, to introduce caching layers within your application design itself. A common best practice is to introduce a caching tier in front of your SQL databases. Here we have a service called ElastiCache, which can give you Memcached and Redis compatible caching layers. So with ElastiCache, you can serve frequently accessed and slowly changing data from this cache in front of your database. So in effect, what you can do is that you can point your database clients, which are your application servers, at the cache, and most of the read requests from the database can be served out of this caching tier, which is in memory. And this will significantly reduce the load on your backend database server. Again, that's cost saving, and you can scale higher because your database backend load will be lower. So cache when you can, at least consider and test using a caching tier. ElastiCache makes it easy for you to manage this in-memory caching cluster. Now, we mentioned database performance. And it's a commonly known fact that at scale, as you reach really large scale for your websites and applications, the data tier scalability is typically the biggest pain point. At some point, you will reach a very large scale, and then data is the difficult one. What you want optimally is to have predictable, fast, low latency performance from your data tier as you scale. And you want this data tier performance to be consistently low. But in reality, what happens is that in many or most cases, as you scale your system significantly higher, your data tier will have degradation in its performance with scale. Then you have mitigating actions. You will take actions like sharding, adding more caching, provisioning more systems, having clustering. Then you have to consider distributed systems, fault management of those. So even if and when you can add the performance and keep the performance of the data tier good enough, you will introduce a lot of complexity, a lot of headaches and management nightmares scaling your data tier. And this is where DynamoDB is really helpful. So by leveraging our NoSQL service, DynamoDB, you can get low latency for your data tier at any scale with close to zero administration and crucially predictable low latency, high performance. So what DynamoDB enables you to do is to have single-digit milliseconds on the DynamoDB side for your read and write requests to the tables. Single-digit milliseconds, consistent performance. DynamoDB runs on solid-state SSD drives, and it's built to maintain consistent, fast latency at any scale. So suddenly, when you leverage DynamoDB, the data tier is no longer the bottleneck. Now let's talk more about scalability. Let's start looking at the application tier again. The first aspect, or the first method that you can do, is vertical scaling. So let's consider your servers which are running on EC2 in this case. They could be your web servers, they could be your application servers, they could be implementing your components or services within your application architecture. In short, you're running EC2 instances or servers. What you can easily do is scale up the performance of these instances by choosing a larger instance type or one with more virtual hardware resources. This is the basic unit of compute capacity in the AWS cloud. It's a basic building block. We have several families of instance types available, all the way from the small, cost-efficient micro instances and our new T2 family with interesting, very handy bursting capabilities, all the way up to compute-optimized, storage-optimized, memory, and even GPU-optimized instance types. So we have a range of easy-to-instance families and different sizes that let you choose the optimal instance size for your particular needs. And this is exactly what you should be doing. Please don't just pick one random easy-to-instance type, maybe the one you have heard of or you're familiar with. What we recommend that you would be doing is to make a rough guess first. So roughly estimate your application needs. How much memory, how much I/O, how much disk space, how much CPU do you expect your different application tiers to require? And then choose one of the easy-to-instance types, but then test it. So implement the load test, put this easy-to-instance under load, running your application tier or service, and then measure it using our CloudWatch service. So measure, meter, and instrument everything. Only by measuring how much you're actually using out of the resources available in the EC2 instance, you know how much you are utilizing it or not, and then optimize it. Using the cloud, it's trivially easy to try, for example, one instance type first of a certain size, run a load test, realize that, well, I seem to have a lot of memory, but I need more CPU performance for this particular single-threaded application, for example. Okay, try a compute-optimized instance. All you need to do is simply reboot the instance with another instance type from the same AMI or application machine image. So it's trivially easy and cost-efficient and fast to try different EC2 instances. So the recommendation is to identify the optimal EC2 instance size and type per application tier. And then, once you have identified that for my different application tiers, these are the sets of EC2 instances that are the best fit for performance and cost, then you want to enable scale out, horizontal scaling. This is really the main principle of building scalable systems in the cloud. With vertical scaling, you will hit the roof at some point. So it's far better to try to enable horizontal scalability. And here the service called autoscaling helps. So by using autoscaling, you can easily add capacity to your application tier, in effect adding more servers or more EC2 instances automatically when you need them, and then remove the excess capacity when you don't need it, for example during night times. So you can right-size your environment based on your actual traffic. So actually, the number of servers or EC2 instances you're running is a function of the incoming load. Don't try to have a static number of instances per application tier. Make it variable based on the actual load. Then you're serving the requests with great success as they are coming in because you don't run out of capacity, and vice versa, you are cost optimized because you release the capacity when you don't need it. So when you use autoscaling, you have different options of how to scale out and scale in, which is then removing the instances. You can do it manually. So if you know that you need temporarily, for example, more capacity in this application group, then you can simply issue a manual operation to add or remove instances from this autoscaling group. You can also have a timed schedule where you have a date and time based action that, for example, on Friday evening at 5 p.m. we have some run happening. Let's add more capacity. So you can time these actions. The one on the bottom left by policy is the most common use case. So here you set alarms and triggers. So you set thresholds, for example, high watermark thresholds to add capacity when your system is under heavy load, and then low watermark thresholds for certain metrics like CPU load, disk or application internal metrics, and then you can release the capacity when your system has a lot of overhead. And autoscaling can also help you automatically rebalance your system for better availability. So the best practice is that you would be configuring the autoscaling group to run across multiple availability zones in the regions that you're using. And then autoscaling can help you balance the number of instances to be even or roughly even across these multiple availability zones so that you have higher availability. So just to recap, with manual autoscaling, you can manually issue a command and add or remove instances from an autoscaling group. With a timed schedule, if you know that you have a processing run happening, for example, you can increase capacity before this load happens. And then by policy, you can automate this by looking at metrics from CloudWatch and then have automated actions to increase or decrease the autoscaling group capacity. And one interesting thing is that by doing the manual or scheduled autoscaling, you can basically pre-warm your system before the load is coming. Your system, based on its design, may take a few minutes to have the new instances running in production. So there's always the boot time, there's the provisioning time for the instance, which is relatively short, there's the boot time of the guest operating system, and then the start time for your application, and potentially some configuration orchestration time to set up the instance properly for the latest code and configurations. So let's say it will take a few minutes for the new instances to actually be running in production, health checked by the load balancer in front. So if you know that you are expecting a very high sudden peak load, you can pre-warm your system, if necessary, by increasing the minimum size of your autoscaling group, for example, with a manual action, before you have this peak. Or if it's a regular peak, you can automate a schedule to do the same. Now, let's talk a little bit more about the data tier again. What you want to do to reach scale with your system is to be able to dial up and dial down all the different resources that you need to run your system. So with Elastic Block Store or EBS, you can achieve this really nicely and easily. So you can dial up the block I/O performance or storage volume performance using our provisioned IOPS volumes. With provisioned IOPS, you can set the performance of your EBS volumes that you attach to your EC2 instances. And currently, you can provision up to 4,000 I/O operations, so read or write operations per second per volume. And if you need more I/O per instance, then you can mount multiple EBS provisioned IOPS volumes and, for example, stripe across them using software striping on your operating system. The current limit is roughly up to 48,000 I/O operations per instance when you use multiple provisioned IOPS volumes. In that case, you will definitely want to use EBS optimized EC2 instances for better bandwidth capacity towards the EBS service. This is really handy for workloads that have high demand for predictable, fast I/O performance, such as running your own databases on top of EC2. And then with DynamoDB, DynamoDB not only provides these consistent single-digit millisecond reads and writes to your tables, but you can also dial up and dial down the DynamoDB table performance. So basically, you can in production increase performance and throughput to your DynamoDB tables if your traffic is increasing. And then, to save costs, you can dial down the DynamoDB table performance when you don't need this capacity or throughput anymore. You can do it as a manual operation using the console, the command line interface, or the APIs with the SDKs. And they're really nice and handy community-provided third-party tools like Dynamic DynamoDB, with which you can achieve auto-scaling for your DynamoDB tables. So here in this picture, we have a picture of Dynamic DynamoDB in action. So the blue line that you can see is the actual write throughput to a DynamoDB table. So you can see that it's varying like a sine wave up and down maybe during the days. Yes, it's 24 hours, so you can see these daily fluctuations. And then the red line is the actual throughput of that DynamoDB table automatically scaled up and down by this Dynamic DynamoDB library. So you can see that it's increasing the table throughput as the actual write throughput is increasing, so that you don't run into performance problems with the table, so that you are consistently serving your data tier at fast enough speed. And then, to save costs, Dynamic Dynamo is then reducing the throughput of the tables at nighttime. Currently, you are able to increase the throughput of DynamoDB tables as many times as you want, and you can decrease the throughput of the tables currently 4 times in a 24-hour period. So during a day, you can decrease the table throughput 4 times currently. Now let's move on. Now, in the next topic, or next rule, number 4, we will be talking about how you can simplify your application architecture leveraging services. And as many of these services you will be leveraging are inherently scalable, it is also addressing the scalability and also high availability needs of your end solution, because many of these services are also internally built to be robust and highly available. So you can offload issues with scalability, high availability, and resiliency to managed services, automated services that are inherently built to provide you scalability, resiliency, and availability. To summarize, basically, with the old way of building IT, with on-premises infrastructure, your teams were spending most of their time, maybe 70, even 80% of the time, simply managing the infrastructure in your data center, keeping the lights on. This is what we call undifferentiated heavy lifting. It's necessary, but it's not advancing the business. And this didn't leave enough time for your teams to actually focus on your business advancing activities, such as creating new features, bringing them to the customers, or fixing bugs in the product. As you outsource a lot of your IT infrastructure to these automated cloud services, you can flip this ratio around. And you can manage these cloud assets and services with a reasonable effort, significantly lower effort because they are inherently more automated. You can achieve much higher levels of automation by leveraging these services. And then this frees up the time and effort of your teams to focus on the business advancing actions. So to summarize, we can take a look at now the overall view of the Amazon Web Services portfolio. So on the bottom here, we have our global infrastructure, so the cloud regions, the availability zones within the regions, and then these CDN and points of presence for Route 53 and CloudFront. That's the physical infrastructure. Out of the physical infrastructure, we provide the foundational building block services, so basic building blocks of most of IT, including compute, storage, security and access control, and networking services and features. So most of the IT solutions will be leveraging these. In addition to these, we have a range of platform services. And you can outsource and offload a lot of the building blocks that you need for your solution to these automated services. So we have, for example, the databases for relational database engines. We have DynamoDB for NoSQL, and we have the Elasticsearch for caching as easily managed services. Then we have analytics services for offline, real-time, and data warehousing. And we have a range of application services that can help you architect and build distributed, resilient cloud applications with high levels of automation and scalability. You will need to use things like queuing systems, orchestration, etc. Maybe a search engine to search your data either internally or to provide your customers a way to discover value out of your system. Then you need to deploy and manage your systems. So we have services for application containers, which is an easy way to achieve continuous integration, continuous deployment, and DevOps flows. We have dedicated DevOps tools like OpsWorks, which can help you manage the life cycle of your application and also construct and build your application out of different layers that you choose. You can templatize your system, so you can have easy copy-paste deployments of standard application and solution templates even across multiple regions. So basically under deployment and management, we have lifecycle management systems for your application, including also monitoring and logging systems. So you have visibility into your environment, and you can make business decisions based on the actual data and actual health of your systems. And as a new array of services here, we have our mobile services, which contain, for example, our identity, data synchronization services across mobile clients and applications, mobile analytics, and push notifications. So to summarize, we have a broad and deep set of portfolio services that can help you build your ultimate solutions and then offload and outsource many of the building blocks to these services. And that lets you focus your efforts on your application feature coding. Now, let's take a look at the next rule. Automating operational management. Ultimately, everything is now programmable. So all the services that we provide out of our regions and availability zones are accessible through APIs or application programming interfaces. So everything you used to do in the past in the data centers as a manual rack and stack and configuration operation is now available with a simple API call. And these APIs you can access through the console, through the command line tools, or using the APIs and leveraging the software development kits or SDKs that we provide for different mobile and server-side programming languages. And because everything is programmable, you can now achieve really high levels of automation sophistication with ease, which was not possible in the past when you had to do manual operations for your infrastructure. So we have a set of services and tools that can help you do this. Here we have a set of AWS services that can help you with your application lifecycle management. On the left, we have Elastic Beanstalk. With Elastic Beanstalk, you can basically run containers of your applications in the cloud. And Beanstalk gives you the highest level of abstraction for the underlying infrastructure. When you use Elastic Beanstalk, you can really focus on your application development and let Elastic Beanstalk worry about building the infrastructure, running it, scaling it, and monitoring it on your behalf for different languages. And today we also support Docker, so you can run any application programming code within the Docker containers, and you can run these Docker containers easily on the AWS cloud using Elastic Beanstalk. You can also run Docker if you want in do-it-yourself mode, if you will, leveraging the EC2 instances. For example, the latest Amazon AMI Amazon Linux AMI that we provide supports Docker directly. All you need to do is sudo yum update, sudo yum install Docker, service Docker start. That's it. But Elastic Beanstalk can even automate this on your behalf, configuring the EC2 instances. Then we have OpsWorks. OpsWorks is a DevOps framework that can help you automate the management and lifecycle of your application, but it gives you more control than Elastic Beanstalk. Elastic Beanstalk has predefined set defaults for running optimally different programming languages and application containers. With OpsWorks, you can construct your application out of layers. And you define the layers yourself. I want Nginx here, maybe I want to use HA proxy, I want this kind of database here, etc., etc. So I have more control. And then with CloudFormation, you can achieve infrastructure as code. So with CloudFormation, you can describe your entire solution on the AWS cloud as a simple template, a JSON formatted template, which is in practice a text file. So by using this text file, CloudFormation can build fully automatically your entire system in the cloud, so it's reproducible, repeatable, and you can store this CloudFormation template in version control alongside your application code. So that is the infrastructure as code principle. CloudFormation can build the system on demand when you need it, for example, for development, testing, or production. Ultimately, you don't have to use lifecycle management systems. You can do everything by yourself, manually, if you will, just clicking around in the console, issuing commands in the command line or APIs. However, if you use the console or command line manually, then you're not achieving the ultimate automation level. That's why I have the box looks slightly different here. I'm not recommending do-it-yourself operations in the long run because you don't have automation then. You need to enable automation end-to-end to achieve high levels of operational efficiency and agility for your business. There are also a range of really interesting community and ecosystem third-party tools available that can help you orchestrate your systems, your EC2 instances, their package management, their configuration, their deployment, lifecycle management. So, for example, tools like Ansible, Chef, Puppet, and Salt can let you do this. And they are significantly better at managing your system's configuration and orchestration at scale than previous generation scripting languages like shell script. So do not use a shell script anymore. Take a look at these tools because they are designed for distributed systems management at scale. So basically with these tools, you can describe the target for your system. The tools know the current state. They will investigate the current state of your system. They will calculate the path, what it needs to take to achieve the target state, and then do the necessary steps it needs to do for your system to reach the target state. So what is this target state? So for example, you may want to upgrade your system to the latest code version. You have a new application version. You may have some security patches that you need to patch to your system. So your new target state could be application version 1.2 with, for example, the latest OpenSSL library. So then you give this target to the system, and then tools such as these can help you reach this, and then they can also report any deviations or problems that some of your units did not reach this target state. You can retry or investigate the problems then. Moving on. Talking about failure now a little bit. So the last rule that we have in the rule book here, rule number 6, is design for failure. What is design for failure? With design for failure, you will be able to implement these always-on resilient distributed systems. And you can implement self-healing capabilities for your application, which means that you don't have to have painful, manual, 3 o'clock in the morning operations for every single thing that goes wrong, because things will go wrong. So let's plan for failures and mitigate them in the design before they happen. You will need to follow some best practices to achieve this. So for example, I was talking about bootstrapping the instances earlier. So bootstrapping means that you will need to automate fully your EC2 instances, package management and configuration as they are booting up. If you need to log in if you need to log into your EC2 instances as they are booting up in order to start your application, you're doing it wrong. Sorry, but it's a fact. So if you have any manual operations starting your servers, then you will not be able to, for example, implement auto-scaling. So by bootstrapping, what you need to do is you need to get your EC2 instances to ask a simple question. Who am I? What am I supposed to do? And then automatically give this role, give this target state to your system and instances as they're booting up. So in practice, what you can do is that you can describe what instances to boot with what configuration using, for example, AppsWorks, CloudFormation, Chef, Puppet, or Ansible. With auto-scaling then, you can maintain the sufficient capacity of your instances, and you can also replace any failed instances due to any hardware-software failure. And with CloudWatch, you get visibility into your system. You need to be able to instrument your system all the way up and down the stack and left and right end to end, so that you have visibility into your system. Otherwise, you're flying blind. And you can also automate many of the recovery or high availability self-healing actions using the monitoring and associated alarms. Ultimately, your goal here is that your application, your solution should continue to function even if some of the underlying hardware-software components or units fail, or if they are removed or replaced. So this is the basic premise of always-on applications. What you need to do is to avoid any single points of failure. Investigate your system design and identify if you have one of something somewhere. One of something is a single point of failure. If that fails, it will have probably domino effects across your system. So always run, for example, at least 2 EC2 instances for any given application tier across multiple availability zones. And then assume that everything will eventually fail and design backwards. And we cannot stress this often enough. We have built the multiple availability zones into our regions for a reason. So please use them. So leverage the multiple fault-isolated availability zones in the regions that you are using and distribute your workload and data across these. As you are using the AWS building blocks, very handily, many of the services that we provide are inherently fault-tolerant by design. You can see many of them listed on the left, and there are some more. And then the rest of the services, like Amazon EC2 instances, individual EBS storage volumes, RDS databases, can be fault-tolerant with the right architectures. So let's talk about that now more. So here we have a picture of an AWS region. We have 2 availability zones here, one on the left and one on the right. First, on the bottom left, we have Route 53. So Route 53 is an inherently fault-tolerant service that is now providing us domain name resolution. So our customers can reach our website and service based on our custom domain name. Then the customers will enter the system through the Elastic Load Balancing service, which is also inherently built in to be fault-tolerant and scalable by itself. Elastic Load Balancing can then health check, monitor, and balance the incoming traffic across the available and well-functioning EC2 instances behind it. So Elastic Load Balancing accepts the customer traffic on the left-hand side. It's health checking your EC2 instances on the other side and sending the traffic to healthy instances. And any unhealthy instances can be automatically replaced. Here we have an auto-scaling group, which lets you then automatically add more capacity when needed and remove it when you don't need it anymore. But in this picture, the auto-scaling group is spanning only one availability zone. So it's not optimal yet. And on the backend system side, we are using Amazon RDS, let's say a MySQL or Postgre database, for example. So here we have a master database in the same availability zone as the servers, if you will. And it's a multi-AZ enabled RDS server now. So there's a master database, and there's an automatically created synchronous hot standby replica in another data center in another availability zone in the same region. So all the writes, all the actions that happen in the master database are synchronously replicated to the hot standby slave. So they are in sync. If anything should happen to the master database instance, boom, in this case, then your application clients, the database clients, will fail over to the hot standby, and the hot standby will be immediately promoted to be the new master. And this is happening transparently because the database endpoint, the host name for the database service that you're using on your client side, remains the same. So the database endpoint remains the same. And in this case, we no longer have a fully highly available redundant database because one of them went kaboom. So as the system promoted the hot standby to be the new master on the right, the system or service will immediately start creating another synchronous replica in another availability zone, so that you will always have these two databases which are in sync. So it will automatically create a new hot standby synchronous replica. And then simply for the auto-scaling, it's trivial to choose the auto-scaling group to simply span multiple availability zones in the region. Then auto-scaling will distribute your EC2 instances roughly evenly across these multiple availability zones. And you will then point your elastic load balancer across both of these. So now we have a highly available and scalable starting best practice reference system here. The next topic I want to cover is loose coupling. So you will want to build loosely coupled systems because the looser your components are coupled, the bigger they can scale. What you want to start thinking is creating independent components that implement only one thing and implement it very well. So not monolithic monster code where everything is in a single code base. You want to decompose your application into individual components that optimally implement only one thing, and they do it very well. Implement it internally as a black box, and then expose it as a service, even internally. Now there's a trend called microservices, where the idea is that your application is internally consisting of multiple individual services implementing only one thing. And then there's a concept called pizza teams, or two pizza teams, where a small team is responsible for coding, operating, running, maintaining this service that they built. So what is a service? So when you implement this application component or code, basically it's providing a feature. It's providing your cool feature, like maybe a recommendation engine or maybe the top 10 list for your game. Now, to make it a service, you will want to expose it through an API, maybe a RESTful HTTP API. And the nice thing when you implement it as a service is that your customers, which are the other tiers of your application, or maybe other applications consuming your service, they are using your more or less standardized stable interface or API. So try to keep the API relatively stable, maybe with versioning if you add more features to your API. But then this lets you hide the internal. You can even change completely and rewrite the internal implementation of this service. Your customers don't know any better because they are simply consuming the service through the standardized API. So this is also decoupling your product teams in your R&D. So basically they can all be iterating on the internal implementation of the service, and they have less consequences because the customers of this component or service are using it through the standardized, relatively stable interface. And as your components are talking to each other, try to avoid direct coupling, which means that your code is making a fixed call directly to another component running in another server or EC2 instance. Because then, if the service you are using, like the orange box on the right, is slow, behaving badly for whatever reason, if you have tight coupling, your client side on the blue box is then waiting and pending. So your thread is blocking. You have TCP sockets blocking, your Java threads are blocking, and then basically one slow service will start slowing down the dependent services, and you have a domino effect going through your application. So you can avoid this by decoupling your components or services with queues. So here you should be using the simple queue service, which means that you don't have to manage your own queuing system, its availability and scalability. So you can simply leverage the existing fully managed service, SQS, simple queue service. So then you can drop the request to a queue, and when the dependent service has time, it will consume the messages from the queue, act on them, and then respond asynchronously. So this will help you scale higher, and you can also avoid these domino effects. The next thing is idempotence, that as you are calling some functions or services through APIs, you need to be able to have retry and fallback mechanisms. And idempotence means that if you need to retry a request, because maybe the dependent service is again busy, not responding properly, then you need to be able to retry, fallback and retry. And as you retry, idempotence means that you can send the same request multiple times, but when the service is actually handling the request, it will only execute it once. So you are safe to retry, it will be only executed one time. Circuit breakers is a concept that you basically need to disconnect some badly behaving services if they simply will not respond. So keep retrying a few times with incremental fallback, but ultimately you need to make a decision. If this service I'm trying to use is simply not available, then use a circuit breaker and say, bye-bye, I'm not using this service now, it's not available, I need to move on. I need to serve my customer request. Either you drop it, don't start buffering it too much, buffer will run out anyway, so either drop the request or move to degraded mode. Degraded mode means that you still handle the customer transaction, but you don't have all the fancy bells and whistles implemented by these services. So have a more simple response. Still serve your customers something. Maybe you don't have this top 10 list. Maybe the recommendation engine is unavailable. But try to still serve the customer request. As the badly behaving service, the green box in this case, comes back, then you can re-enable this and go back to the fancy feature set. Ultimately, when you do these microservices, so implement your components as individual services, you can load balance, auto-scale, monitor, and high availability assure each of them separately. So if, for example, the yellow service tier, which is maybe the recommendation engine, needs more capacity, then you can auto-scale and add more capacity only to that tier, which is cost-efficient because the other applications tiers do not need additional EC2 instances. The next point is separate your state from your processing. So keep your state, session state, and persistent data away from the compute instances. So when you are load balancing and auto-scaling to a dynamic number of EC2 workers, you will want the session state of your customer, like a shopping cart or game state, and then the persistent data that they are using somewhere else. And here we have handy services like S3 for storing the persistent data objects, and DynamoDB and Elasticache, which are really handy and often used for these session state storage. So then the workers will simply store the session state after the transaction in this service, like DynamoDB, and the next worker, randomly selected by Elastic Load Balancing, if you don't use session stickiness, will simply fetch the session state from DynamoDB and continue with the next transaction. And then test it. Don't assume that your design works even if you try to follow all the best practices. You need to verify it. So verify your design by actually injecting and generating failures into your system. So here we have our friends at Netflix who have designed and implemented and even open sourced many handy tools that can help you do this. So you may have heard of Chaos Monkey. So with Chaos Monkey, you can introduce failures into your system. So it can randomly shoot down individual components of your system, and you can verify what actually happens if you lose individual components or units. This is called the game day practice, where you actually test injecting failures into your system, and you see that your software design and your business processes can overcome this without causing customer visible disturbance. The next interesting simian or monkey they have implemented here is called the latency monkey. And apparently, according to Netflix, this is even harder than the Chaos Monkey. Chaos Monkey simply destroys things. Latency Monkey makes these microservices slower. So it can start introducing slow responses between your application services and tiers. This is much more difficult than to overcome, but it's a good idea to test this if you can. The next monkey that I highlight here, the conformity monkey, is not destroying things, but it's really interesting and nice to have in a distributed system. So Netflix has built the conformity monkey so that they can detect system entropy and drift. So as your application is scaling, it's built out of multiple services or microservices, it will start becoming a complex adaptive system. So it's a distributed system, it's complex, and it's adaptive. Adaptive are these self-healing capabilities. So in a complex adaptive system, there will be state changes, there will be entropy and drift. Things will not always go exactly as planned, and many of the actions that cause these drifts can be automated. So you want to know what is the current state of my system, and are all the instances of my application, for example, for the recommendation engine, exactly the same? Or are there differences? There shouldn't be. They should all be implementations of the same known good state. So they built the conformity monkey so that they can see the drift in their system. And then, for example, they have the janitor monkey to clean unused resources. Ultimately, here's the rulebook. So I really hope that you enjoyed it. I hope it gave you some good ideas of what to look out for, what to do, what maybe not to do, as you start designing these scalable, available, resilient cloud applications. So ultimately then you can provide your users with elastic utility capacity, leveraging a highly available global coverage. You can achieve higher business agility by automating your lifecycle and operations. And then you can personalize your applications by leveraging our cost-effective storage and then the big data and analytics services that we did not cover today. But if you're interested, please join our big data and analytics sessions. So thank you very much. If you need to find out more, if you want to find out more, please visit aws.amazon.com. Remember, you can get started with the free tier. Thank you very much. I'm Markku Lepistö. And now let's move to the poll. So now I'll ask my colleague Rusit to start the poll. So now please vote on what you want to find out next. What do you want us to do next? So in the poll, you can now choose whether you want to see next topics like developing mobile apps with AWS, or do you want to run your applications and websites without any servers, or do you want to look at the AWS command line interface like a masterclass of CLI, or do you want to have a security specific topic? So let's let the poll run for a short while. Still, we can see the answers flowing in, so thank you for that. This is exactly how we love your feedback, and we are iterating our services based on your direct feedback. You can see the poll running. Let's let it run for a short while still. Thank you. Some topics are catching up. It's almost like a Formula 1 race here. Okay, let's stop the poll here. Thank you very much for everybody who replied. So the winner is developing mobile apps with AWS. I personally think it's a great choice. All of them are nice, but thank you everybody who voted. The reason I say I think it's a great choice is that very recently we have announced a lot of interesting mobile related products and services. So let's do that next. Thank you so much. And we still have the survey at the end, so please don't forget to complete the survey. Thank you so much. It was really a pleasure. I hope you enjoyed it, and I hope you see you next time when we talk about mobile services. Thank you and goodbye.